Okay, so the phenomenon we just saw, namely, if u cross v is dotted with either u or v, you get the zero scalar. That's true in general. So what we end up getting, and this is really, I guess, the answer to the interactive question, is this theorem. For all 3D vectors u and v, if we define w to be the result of the cross product, then w is perpendicular to both u and v. Can you imagine this in three-dimensional space? So here's a question that we can ask now just to practice some of these things. So I've got the point A, point B, point C. We create the vector u from point A to point B and the vector v from point A to point C. And I'd like to find a vector that is orthogonal to both u and v. So first of all, we need to find the vector from A to B and the vector from A to C. So we should subtract, but of course in the correct order. And so vector u will be -1, 2, -1, and vector v will be -4, 5, 2. Now, if we want to find if you take these two vectors, I mean, you can sort of imagine if you just even using two fingers sort of create a V shape with your hand, and who knows which direction you need to rotate your wrist for this, but if one finger, maybe your pointer is this vector, and then your middle finger is the next vector, then you need to those two vectors would span the shape of a plane, and you need a vector that's going to be perpendicular to both, and you can use a finger on the other hand to represent where that other vector would have to be. And this is how we would compute this on paper. We create this 3 by 3 determinant. It's written as an alternating series of 2 by 2 determinants, and in the end here we'll get 9, 6, 3 as the vector. So you should really check that this vector n right here is perpendicular to both of the original vectors that we started with. So here's my attempted picture of that. So we had the vector u from A to B and the vector v from A to C. And so these two, this is meant to be a 3D picture, but I realize it's on a two-dimensional piece of paper. But this vector, and then perpendicular, it goes this way. So I mean that there's a right angle there and there's a right angle there. And it's hard to draw these things, but this is the best that I can do on paper. This is what I would have drawn on a whiteboard anyway. Okay, one other thing to note from the previous example, again, this was the setup and then how u and v were defined and then how we computed the cross product. If we computed v cross u instead, we would actually get -9, -6, -3. So take a look at how similar and how different that is to u cross v. So u cross v versus v cross u. There's something to notice here that's true in general. For any two 3D vectors, the cross product of u and v and the cross product of v and u are actually opposites of each other. In other words, these two vectors will point in opposite directions geometrically.